So, welcome back to the session of Power Electronics and Instrumentation. We were discussing about the different digital voltmeters, right. So, in today's session, we will be discussing the other available digital voltmeters which we are going to make use of in instrumentations. Okay. Another type of digital voltmeter that we can use is nothing but using the direct compensation method. Direct compensation type digital voltmeters. So, in this type of direct compensation type digital voltmeters, we are going to make use of the reference voltage, that is the input that has to be measured, it is continuously compared with the staircase voltage with a defined value of the number of the step size. So, depending on that, when it reaches the final value which matches with the applied input, then we are going to say that this is the amount of voltage that is available from direct compensation method. Okay. So, here initially it is also known as the staircase type. Okay, we call it as a staircase type of DVM, since we are going to compare directly with the input, that is a step size will be compared depending on what are the parameters. So, this is the block diagram of the direct compensation type. So, here it consists of a counter, okay, which is set and reset, a reference voltage, and then an input comparator which is continuously comparing with the input voltage, and depending on what is the input voltage, this gate, an AND gate is used which allows the signal to flow through, and it opens the gate such that the clock we are using to generate the pulses, an oscillator circuit. So, that will allow the pulses to flow through the gate. How we are going to monitor it step by step? We have written here. That is, initially at the start of the conversion process, we are going to keep counter is equal to 0. So, at the instant, let us assume T1. Now, you can also see the staircase waveform where it starts at T1 and it follows up to the end of the process, that is T2. So, this complete range from T1 to T2, how many number of counts is being addressed, that will be taken as the input voltage. Okay. So, initially at the start of the process, counter is equal to 0, resetting at time T1. Once the counter is equal to 0, the DAC output, whatever you are going to get the output from a DAC will also be equal to 0, because we are not going to give any input. Fine. Next, if the input voltage is not equal to 0, we are continuously using a comparator, input comparator is used. Okay. So, we are finding out whether the input voltage is not equal to 0. If this condition is true, if it is equal to 0, the input comparator will not give any pulses to the gate. Okay. If it is not equal to 0, some value higher than 0 if we are going to apply, then input comparator opens the gate, sends a signal, output signal telling that there will be a change of state which lets the gate to be opened. Once the gate is opened, what happens? This clock that is generating the pulses will be allowed to pass the pulses through the gate to the counter. That is the next process. So, the clock pulses are generated, the counter the clock pulses generated are going to the counter and then through the gate. If the gate is open, only then the clock pulses will be let into the gate to the counter. Once you get into the counter starts counting. Okay, till where this will happen? Till the DAC output voltage is obtained. Till where? Now, when you are obtaining these DAC voltages, there will be a small step variation. Okay, this small step at each count will be introduced. Okay, depending on the reference voltage what we are going to choose, we can vary the step size. Okay. Next, the result whatever we are going to obtain from this type of direct compensation. We are giving the voltage to the input comparator, which directly is making use of the gate. Depending on the state of the output of the input comparator, we are going to check for the change of state. Okay. If the input signal is starting from 0, which if it is not equal to 0 and if it is some other value greater than 0, then what happens? This input comparator changes its state, gate is open, clock pulses are being flowing from through the gate to the counter, counter starts counting the number of pulses generated. Okay. When these pulses are being counted, the step size whatever we are going to get, or the output whatever we are going to get, represents a staircase shape. Okay, step by step shape. That is why it is also called direct compensation type DVM are also called as staircase type DVMs, because we are finally ending up at generating a staircase type of waveform. Okay. Now, whatever the voltage is obtained is a staircase voltage, the process continues. Till where this process continues? Till the voltage across the staircase will be equal to the input voltage. Constantly be comparing. Now, till where we can compare this? Till the input, that is whatever the comparator output we are going to get, that output changes the state. Comparing with the reference value, the comparator changes its state. Once the state is changed, what will happen? Automatically a signal is allowed to go to the gate pulse. Once the signal is going to the gate pulse, what happens? Gate is closed. Once the gate is closed, what happens? Whatever the clock that has generated the pulses will not be sent to the counter through the gate, as gate is closed. So, what happens? From this instant of time when the gate is closing is taken as T2, time 2. So, what are the counts that you have measured from the time instant T1 to the time instant T2? Those number of steps is directly proportional to the input voltage. So, the input voltage Vi is directly proportional to the count voltage that is developed, the number of count, or is directly proportional to the voltage that is generated due to the count signal. Okay, so this is how we are going to find out, or we are going to find the value of the voltage using a direct compensation method. As we are interested in finding the different types, as we are interested in studying the different types of DVM, this is another type of digital voltmeter. Now, some of the advantages of using this type of direct compensation type DVMs are, the first one is the input impedance of the DAC is high. Okay. So, when the compensation, when final after the process is completed, when the compensation is reached, the input impedance of the DAC is very high. That is one of the main advantage. Another one is accuracy depends on the stability of the voltage that is generated, on the stability of the DAC output, the voltage across the DAC output that is generated, that is directly proportional to the accuracy, whereas the clock circuit whatever we are using does not have any effect on the system accuracy. Okay. So, these are the main advantages of using a direct compensation type digital voltmeters. Next, let us see some of the disadvantages. So, one disadvantage of using the direct compensation type of DVM is the system measures at the end of the compensation. Then what happens is the system starts measuring the instantaneous values of input signal. Okay, means the reading what we are taking down is unstable. So, the reading at the input signal as the compensation is reaching, that time the reading will become unstable. So, this is a disadvantage of using a digital voltmeter. Now, the next type of digital voltmeter which we are going to study is about the successive approximation type digital voltmeters. Okay. Now, approximation means what? Now, we all have gone to the vegetable vendors, and nowadays we use everywhere is the digital display weighing machine. Previously, we were using something like this, say at one end, okay, a weighing machine, hand weighed machine. Okay. Now, you want to measure some quantity. Okay, let us say this is the quantity that you have to measure. So, what we were doing to balance this weight, if you hold it like this, since the weight is more, it will tend towards this side. So, let us say for example, we are going to place weight weighing some 1 kg. If suppose the object placed is equal to 1 kg, it will be in a stable, this point will be stabilized, right. If suppose the weight is more than this 1 kg, then what will the vendor do? He will remove the 1 kg weight and add the next point, that is 2 kg weight. Okay. If suppose this weight, the input whatever we are giving is less than 1 kg, the previous one what we had in kept it here, what will happen? He will remove the 1 kg weight and then he will say some 500 gram weight will be placed, isn't it? This is the operation what we are going to do to balance the weight, approximate, trial and error method. Yes or no? So now what we do? Depending on the balancing, it should be steady line, it should be in a balanced condition. So we are adjusting the weight. Now you can see, let us consider this as this is the output which we want to measure. Okay, for this output that has to be measured, now this is the input what we are balancing. You are giving some input here. Now let us say for example it was 1 kg input. So when V in was less than V out, now 1 kg was very less, this point which we want to measure is a high value, then what we do? We remove this and place another extra bit. We remove this 1 kg and we are adding 2 kg weight, isn't it? So what you are doing? Remove this and set the next bit. Similarly, now if the V in, now if 1 kg was a very big one which is bigger than this, 1 kg is bigger than what we are going to measure. Now what will happen? When V in is greater than V out, we are going to reduce, replace 1 kg by 500 gram weight. Now in between this we are going to add some 100 gram each bit by bit, and we are going to see whether this output and input is in a balanced condition. This is exactly the process, the weighing of any device using the hand weighing machine. This is the exact process what we carry out in successive approximation type of digital voltmeters. Now I hope you have understood this concept. Okay, just imagine the situation how you are going to balance the weight. Similarly, here also in case of the digital voltmeters, initially keeping the same concept, we will analyze how we are going to find out the approximated value. So you can see the block diagram for successive approximation type DVM, which consists of an input comparator, a sample and hold circuit, and then whatever the input we are going to take, we are going to measure across the DAC, and using the reference voltage we are going to feed it to the DAC, and then from the counter, see from here start and stop pulses are being generated. At the start of conversion the entire process takes place, that is a counter is being initiated, and depending on the DAC output voltage it will be measured. Now how we are going to measure the process? Successive approximation. Constantly one after the other we are going to check the weights of input and output. Okay. So comparing the output of the DAC with respect to the input that is available, we are going to see bit by bit. Okay. So we have to follow a trial and error process where we are going to get the approximate value. Okay. So let us take any input value you can assume. So let us take the value input Vn. Okay. The operation is the same, you are giving an input, you are using the sample and hold circuit, and this is the process of taking place, the conversion. Finally the digital readout shows the value of the output voltage. Now how this process takes place internally? Let us see with respect to the table how we are going to calculate the different values for, or how we are going to measure for any given input voltage, what is the approximate value of the output voltage. Now the previous one you have seen the process, right, where you are going to compare initially the DAC output. When the counter is reset to 0, you know that the DAC output is also going to be equal to 0. Okay. Now let us start with the operation. Let us say this value what we are going to use is 51. Okay, I am writing it in decimal numbers. Here we have taken, as it is a digital operation, it is a binary number system, so we are going to use zeros and ones, which represents, let us say for example, input is 51. You can take any value and find out the approximate output voltage. Okay. Now, operation. First, initially the DAC output, this is the DAC output which we are going to get. Let us assume that the DAC output is going to be 0 initially when the counter is reset. So, now what we are going to do? Set D7 bit. D7 bit is set. Okay. Now, set means 1. Already it was in 0 condition. Now, what you are doing? You are setting D7 bit. So, 0, 0, 0, 0, 0, 0, 0. So, let us write the powers for this, the values, the weighted codes for these different 8-bit symbol. Okay. So, 2 to the power of 0 represents 1, 2 to the, just for our understanding, okay, 2 to the power of 1 is 2, 4, 8, 16, 32, 64, 128. These are the values at which it represents. Okay. Now, D7 is set. Now, what you have to do at this point initially, you have to compare input with the output. Remember the weighing scale. The same principle we have to adopt it here. Now, okay, here input is given. This is the output which we are getting from the digital output. So, 51, 128 is the code. See, can you find anywhere else you can find 1? No, you are finding 1 only at the bit D7, MSB bit. So, what is the value it is carrying? 128. So, now can you tell me 51 input V in, what is happening to V in? Is it less than or greater than 128? It is less than 128. So, what is the condition? What and all we are going to compare? Now, you can say that V input is less than the V output, DAC output. If it is less than 1, what you have to do? If V input is less than the V output, then reset D7 and set the next bit. So, here what is the output you are going to do? D7 is reset. Okay. So, what you are going to do? You are going to reset. Reset means make it a 0, set the next bit. Means when the input is lesser than the output, what you are going to do at the input side? The weights, we place a 1 kg weight now. Now, the output what you have placed is a higher weight. So, what you are going to do? You are completely going to remove this and you are going to add a new weight, because it is very less than that of the output. The same thing, you are completely removing this bit, adding the next bit. So, what you are doing? You are going to add a new one. When this operation takes place, initially whenever we say a digital input, usually we take the output voltage as 5 volts. Yes or no? 5 volt is the standard value which we are going to take for a digital signal. Now, at the start of the signal you used D7 as 1. So, what happened? You have to take the V value, V reference divided by 2. So, 5 divided by 2, you will be getting 2.5 volts. This will be the output voltage available. We have to compare this voltage what we are going to get. Okay. Now, next what you are going to do? Here, let us say we are taking Vn is equal to 1 volt. This is the bit which we are taking it to compare. Okay. Now, we have to, after approximating, we have to approximately get equal to Vn is equal to 1. This is at the input of the comparator. Before the sample and hold circuit, we have the input. There, we are taking 1 volt. This is the bit what we are going to compare within the block diagram, whatever we have seen. Okay, understood now? Next, we are going to the next step here. So, next what you did, since Vn is less than Vout, you reset the D7th bit and you are going to D6 bit is set. Fine. Now, what is going to happen? 0, 0. The others follow the same method. 0, 0. Now, what is the value of D6? 64. What is the bit you have taken? This bit carries for all the conditions. Here also 0, 0, 1, 1, 0, 0, 1, 1. Next bit also 0, 0, 1, 1, 0, 0, 1, 1. This continues till all the 8 cycles is completed. Now D6 bit is set because Vin is less, you are resetting D7. Followed? Next what you are going to do? Compare 51. This value is 51. 51 is less than 64. Here 51 was less than 128. This is only for your reference. You should write only it in bitwise. Okay. 51 is less than 64. So 51 is less than 64 means what you are going to write? V in is less than V out. So you should reset the bit D6 also. You have set it before the operation. After you perform the operation, after the comparison, you are going to reset the D6th bit. Followed? Now what about the voltage? V reference you divided by 2. This voltage 2.5 you can divide, you have to divide by 2 again, okay, because you are doing a right shift operation. Okay, you can either take 2.5 V reference divided by 4, or you can also do 2.5 divided by 2. You will get, what is the value you are going to get? 1.25. So I will write it here, 1.25 volts is the output which you will be getting, 1.25 volts. Got it? Followed this step. Next you have reset the bit. Now the next cycle, where since this is V in is less than V out, you are going to clear this, add a new weight. Okay. So again D5 should be set now, new weight should be set, 0, 0, reset this, set bit 5, 0, 0, 0, 0, 0. What is the value? 32. What is the value we have taken here? 51 is greater than 32. Now the condition is V in is greater than V out. V in is greater than V out means what happened now? You have to keep the bit S5, D5 in the set mode only. Follow, you are not going to change because it is less. For this now you have 500 grams. On top of 500 grams you are adding a 100 gram weight and checking for the balancing condition. Okay. Similarly here, once the condition is V in is greater than V out, what we are going to do? Keep the bit as it is, no need to reset it. Okay. So during this condition you are not going to reset the bit, D5 is in the set mode itself, D5 set mode. Now what is going to happen? Since you are already done this, VR divided by 4 you can do, or you can take 1.25 divided by, that is VR divided by 8, or you can also use 1.25 divided by 2. This is step by step, by 2 by 2 by 2 you will get 8. So 0.625. Followed, how you are getting the output voltage? 0.625 you got. Coming to the next step, D5 should be set. But for the next clock pulse what you should do? This will continue, okay, the number of bits. Now here you should set D4. So 0, 0, should this D5 should be as it is, whereas D4, take it like this, okay, 0, 0, 0, 0. What is the value? 32 plus 16, you will get it as 48. So 51 is greater than 48 in this cycle. So what happens again here? V in is greater than V out. What should happen to D4? D4 should still be in the set mode. Now you see here, for this value you got 0.625. Okay, for this you should again divide by 2. So now what you are going to do? 0.625 is already the value what you have got here. You are not going to do divided by 18 because here we have two different bits and the condition changes now. Okay. So now what you are going to do? 0.625 was the value which you got for this position, D fifth bit single bit. Now divide by 2 the same value. After this you have to add the weight. So 0.625 divided by 2. Check what is the value you are going to get. 0.9375 volts will be the approximate value. Since V in is greater than V out, again we are kept the D4th bit also as in the set mode itself. Next, D3 should be set for the next clock pulse. So now what you are going to do, 0, 0, keep as it is because input is greater. So keep this, set the next bit, D3 bit you have to set. So the remaining will be 0. Now see the value, 32 plus 16 was 48, 48 plus 8, 56. So now 51 is less than 56 in this condition. So what happened? V in is less than V out. So what you have to do? You have to reset the bit D3. This should become 0. D3 should be reset. Since when you added this weight, again it became more. So within, this is the maximum limit, this is the minimum limit. Now you should replace with the lesser weight object should be kept so that it will reach the balance condition. The next step what you should do, D3 should be reset. Now calculate the value here. You got 0.625 for this, 0.625 divided by 2 you got this, 0.625 divided by 4, add all the values to get the total weighted approximated value. So you will get 0.625 plus, the first bit was 0.625 plus 0.625 divided by 2 plus 0.625 divided by 4. I hope you are understanding this logic. Okay. 0.625 plus 0.625 divided by 2 plus 0.625 divided by 4. So find out what is the value you are going to get for this. 1.093 volts will be the value. Okay, so 1.093 volts will be the value, approximated value which you are going to get. Now, what happened here? V in is less than V out, so you have to reset the bit D3. So the next cycle what you should do? D2 should be set. 0, 0, 1, 1, reset bit 3 from the previous one, set the bit D2, 0, 0. Okay. Now, see, check the value. 32 plus 16, 48, 48 plus 4, 52. So here 51 is less than 52. Okay. So 51 is less than 52. What will happen now? V in is less than V out. So D2 bit should also be reset. Followed, D2 bit should also be reset. Now how will you calculate? 0.625, 0.625 plus 0.625 by 2 plus 4 is not considered here. Here we have a 0. So 0.624 divided by 16. Okay, so you will get it as will you write this? 0.625. Shall I tell the last time? This the same thing will continue. But here you are not going to add 4. Okay, let me write it completely. Here 0.625 divided by 2 plus 0.625. You can see here 0.625 was this value. Next 0.625 divided by 2. This is divided by 4. Here we have 0, leave it. Next you have to divide by 8. Yes. So 0.625 divided by 8. See what is the approximated value. Till where you have to do this process? Till you get till the balancing what you are doing is in a steady state. Okay. So what will be the value here? 0.015. 1.093. See here you can see you are going to achieve stabilization from 9511, almost it is in the 1 volt only. Okay. Now next what happened here? D2 you should reset now. Why? Because V in is less than V out. So next bit is D1 should be set. Okay, so for D1 to be set, 0, 0, 1, 1, 0, D2 should be reset, D1 should be set 0. So again same procedure, 0.625 plus 0.625 by 2 plus 0.625 by 16. You have to do that. Okay, do the calculation and find out what is the value. Now let us see with respect to the decimal value. 32 plus 16 is 48. 48 plus 2 is how much? 50. So 51 is greater than 50. So what happened here? V in is greater than V out. Following how to do? Now Vin is greater than Vout. So what happens to the D1 bit which is set? D1 should be in the set state. How will you calculate? Apply the same principle. Okay, after applying, tell me what is the value of the voltage you are getting. So here approximately 0.976 volts you are going to get. Okay, continue the calculation process. Next, Vn is greater than Vout. If it is greater than Vout, what you are going to do? D1 is kept in the set mode itself. Now the last step, D0 should be set. Should complete 8 cycles because 8-bit output we are taking for a DAC. Okay. So here what happens now? 0, 0, 1, 1, 0, 0. D1 should be set because Vn is greater. D0 should also be set. Now you compare 0, 0, 1, 1, 0, 0, 1, 1, is it not but this same thing? 51 is equal to 51 reference voltage. So what you are going to get now? Vin is equal to Vout. So by approximating, by taking a value, approximating the circuit, we are going to obtain for so many number of steps, the input whatever we have applied will be equal. Okay. So now what you have to do, since it is equal, D0 will also be in the set, keep it as it is, keep it in the set mode. Okay. So approximately 0.99 some value you will get the volts. This was the input voltage what we had applied, Vin, that is equal to 1 volts. Followed how to do, this is the procedure you have to carry out. Okay, you can take any value here, use it and compare it. Okay. Whatever the input voltage you had given initially, you will be getting that after 8 clock pulses. Okay. So this is about the table for successive approximation type digital voltmeters. I hope you have understood it. Only if you write and practice, you will understand how this bit has been shifted and what is the operation we are going to do. Okay. If you didn't understand it, just repeat the video and play it and see, because this is very important concept. Not only here, wherever you speak about digital electronics or the higher semesters, wherever you are going on, you will be using the successive approximation type at different levels of point, okay, at different levels of time. So you need to know the basic concept of how we are shifting the bits and how we are going to get the voltage. Here also in this, when we are doing this process, you can see here we have some delay. Okay, so we in the initial step, you might have seen in the block diagram, we are going to make use of a sample and hold circuit. Here sample is nothing but we are allowing the capacitor, we have a capacitor circuit as you can see here, the capacitor is charged during the sample period. Okay, and once after the sampling is done, when the switch is shifted to the hold state, okay, what happens? The capacitor discharges. So the actual conversion that is taking place is in the hold mode. When you keep the circuit in the hold mode, this operation is carried out, okay, in the sample by making use of a sample and hold circuit. So these are the different types of digital voltmeters which we have for our syllabus.